Problem number 4 states, back in the day, telephone calls and other data were transmitted with microwaves with a wavelength of 3 centimeters. Modern data transmission uses lasers and fiber optics. The commonly used lasers have a wavelength in vacuum of about 1 micron, or 10 to the 6 meters, and assume the speed of light in the glass is the speed of light divided by 1.444, and they want us to note the frequency of light will stay the same in the glass as it was in a vacuum, but its wavelength will be longer than the 1 micron. And for part A, they want us to calculate the frequency of the microwave with 3 centimeters. So, started out by listing our variables given to us. We have our wavelength of the microwave at 3 centimeters, which I converted to 0.03 meters. We have our frequency of the fiber optics, or wavelength of the fiber optics, at 10 to the negative 6 meters. And then we have our speed of the fiber optics at the speed of light divided by 1.444. So speed of light is equal to 3.00 times 10 to the 8 meters per second. And if we divide that, we get 2.08 times 10 to the 8 meters per second for the speed of the fiber optics. And then just to visualize the difference in the size of the wavelengths, I've drawn the microwave here with the wavelength of 3 centimeters. You can tell they are much longer distances between wavelengths, or much longer waves. And then the frequency of the fiber optics obviously has much smaller wavelengths. So it's traveling slower, but at a higher frequency. So we can calculate the frequency by just dividing the velocity by the wavelength. And for our microwave, we know that it's moving at the speed of light because it's electromagnetic waves. And so we just want to divide that by the wavelength of 0.03 meters. And we get 1.00 times 10 to the 10 hertz, which we can convert to 10 gigahertz. So the frequency of the microwaves are 10 gigahertz. And for part B, they want us to calculate the frequency of the laser light used for the fiber optic transmission. So same thing we did in part A, except this time we're going to use the speed of the fiber optics, which we calculated to be 2.08 times 10 to the 8. And then we get the frequency at 208,000 gigahertz. So much faster than 10 gigahertz, or much higher frequency. And then part C, they want us to calculate the ratio of the two frequencies to find the relative rate of information transmitted by the two methods, because the amount of information that can be transmitted in a given time is proportional to the frequency. So for that one, I just took our 208,000 gigahertz divided by the 10 gigahertz, and we can see that the rate of information transmitted by the fiber optics is 20,800 times faster than the rate of information transmitted by the microwaves. And then finally, they want us to calculate how long it will take such microwaves to travel 100 kilometers, and then how much faster will it take, or how much faster will the microwaves cover the 100 kilometers than a signal of fiber optic cable of the same length. So for that one, I've just taken our 100 kilometers and converted it into meters. And then we can just, for the microwave, take, we know for every 1 second, the waves move 3.0 times 10 to the 8 meters. And then so we just times that by our 100 kilometers, and we know that it will take 3.33 times 10 to the negative 4 seconds for the microwave to cover 100 kilometers. And then doing the same thing for the fiber optics, except using its speed, we get 4.81 times 10 to the negative 4 seconds. So just a little bit slower. And that difference in speed is 1.48 times 10 to the negative 4 seconds. So it's going to take the fiber optics that much slower to go 100 kilometers than the microwaves. And this all ties into what we're learning in chapter 16.5 about electromagnetic waves and microwaves.